So this will be the overview of this presentation today. We will learn about what is prestressed concrete, a bit about its history, and we'll try to dig a bit deep into what are the types of prestressed concrete, what are the terminologies involved, and about materials. Probably this introduction will give us a better understanding of prestressed concrete. After that, we'll try to go a bit deeper and we'll try to see what exactly prestressed concrete mean and how does the physics work, what is the advantages, and so when we use this in a structure, what exactly, how exactly it helps us. So this first two part actually is the main mood of this presentation. And then we'll quickly go through current state and applications, how it's being used currently, applied currently, and what are the current ongoing research or ongoing aspiration, how to improve this prestressed concrete. So what's the future of this? And then at the end, we can quickly talk about what are the career opportunities. And if you have any comments or question, we can talk about that. Throughout the presentation, if you have any question, feel free to note them down. And then I will try to go through them at the end. Let's get into what is prestressed concrete. We often hear that, hey, there is a precast structure there, or we always keep hearing there is a prestressed bridge coming up, or they are using prestressed material there. So what exactly is prestressed, and why concrete always comes after prestressed? So from the way we see it's literally pre-stress is basically a combination of pre and stress. So before we actually load the structure for its service load, we erect it, and then we connect all the members. And after that, before we start applying the intended service load, we actually stress it before that. So that's why we call it pre-stress. And we intentionally, deliberately create a permanent internal stress in the structure to improve its performance. Let me quickly turn on my pen so that I can. In usual reinforced concrete, we always have some tension reinforcement, because this is very common. I think most of you know that concrete is very, very poor in taking tension. In fact, there are only a few materials which can take tension, mostly soil, stone, all these things. They are very good in taking taking compression, but they are very terrible in taking tension. Whereas timber is not, the compressive strength is not as high as concrete, but at least timber is a bit versatile. It can take both compression and tension. That's why sometimes it comes really handy. Whereas concrete is very terrible in tension. So wherever there is a tension in our structural design, then we definitely need something that will eliminate tension. And that's the whole concept of reinforced concrete, adding reinforcement wherever we expect tension. Now, but the problem with that is that before even steel comes into play, we have to crack the structure, crack the section. Because if you remember our classic reinforcement concrete design, then we have compression on the top, right? We have compression on the top, tension in the bottom, and then we have equilibrium where tension is equal to compression. And then after that, when you have tension controlled section, if you keep bending, then only the steel really comes into play, and then it yields, and then structure fails. Whereas we want to help the reinforcement in the structural capacity of a member before even we start cracking. And that's where the concept of pre-stressed concrete helps. We'll dive into a bit more. We'll see how exactly it works. We'll look into the cross section. We'll look into the free body diagrams. But before that, let's talk about why we need pre-stressed concrete. What's the advantage? And we have so many material existing out there. We have steel, we have timber, we have composite materials. Why do we need pre-stressed concrete? So if we look at this structure on the right, this is a pedestrian bridge. Currently, it's being built in Seattle, and there the demand is that the structure which is being replaced has to match the theme of the current existing structure in the neighborhood. So they need something like, so if you look at the right, road, and then if you look at the underside of the structure, then it's kind of flush, and it looks kind of, there are some painting right there. You probably might be able to see there those lights, and then lots of vegetation on the structure. It's curved actually in all directions, and there are ramps. So it's pretty complex structure. So in order to design this structure, we need some kind of material which is cast in place, because definitely you can't have all these complex precast material. It's going to be very tedious. And then most important part here is that quick erection, because this neighborhood is one of the most popular. It's Seattle downtown. So definitely you cannot have a lane closure for more than few days. It's going to be very chaotic and very difficult. So you need something which is time saving, like accelerated construction. You need something which can have longer span. So you can see I try to nail down how the structure might look like. So you can see there are like two spans. You can see actually there are more spans. It's continuous, but you can see two spans here. And I guess each span is around like 200 feet. So you definitely need something which can bear structurally around 200 to 250 feet span. And it's huge, wide, around like 100 feet wide. Prestressed concrete is answer to all this question. So if we need a long span, time-saving, accelerated construction, efficient, slender architectural elements, and it doesn't matter how complex it is, it's possible with prestressed concrete. We will look into this in detail, but I just wanted to give you a quick look of how does actually a prestressed concrete structure looks like. And then there are also various different advantages. Being a concrete, we are a little familiar with concrete because we have been dealing with concrete for a while. So it's a bit more reliable than any other new novel structure. And also we have option of re-strengthening and rehabilitation. And since we build a lot of concrete structure, we have a scope of large and rapid productions. I took it from FSWA manual, and you can see that what's the scope of prestressed concrete. We can go up to, if we generally we do PC girders, which is like around 200 feet, which is about the most of our need, around 100 to 200 feet. Even if we want to go higher and longer, we can have cast in box, which can take up to like 250 feet. And then you can see cable stayed and balanced cantilever box. It can even take you more than 1,000 feet. If we can quickly summarize, prestressed concrete can actually cater to most of the span length. 1,000 feet span length is probably like 99.9% of the structure. So prestressed concrete can cater to all the span lengths, and probably these span lengths are not possible with all kinds of structures. Steel can probably go a little longer than prestressed, but not like as high as 300 or 500 feet long. Obviously, definitely not with timber. Quickly, let's talk about history of prestressed concrete. We can summarize the history of prestressed concrete in 4 phases. In ancient phase, where it was more like intuition. For example, if you look at the medieval boats, they used to have the mast and tied from all sides. So anything that is pre-tensioned or pre-tied, we can probably call it prestressed. So in that sense, we have all those structure. But second stage is mostly rationally understood, mostly rationally see where the tension is coming and how you can eliminate that tension. But the problem at that time was there was lots of physics involved, which involves the losses. That was not understood. They didn't know it's coming. So most of this structure in second stage, it failed, even though their concept, their idealization was okay. And then the third phase was the early 90s, late 90s, where we had some kind of prestressed structure, but they knew that there is a loss, there is a creep loss, shrinkage loss, relaxation loss, but there were not enough strong material to cater to those losses. And then fourth stage, probably I would call what we call the modern prestressed concrete, where we kind of quantify the loss exactly, at least as much as possible using different models, and then come up with some high strength material. And we are still evolving. We are still trying to minimize loss, come up with new materials. Now let's look into what are the types of prestressed concrete. Mostly we keep hearing this word precast or PS, prestressed, PSC. So PSC is a very popularly used abbreviation for prestressed concrete. And in structural world, we use PT a lot. We just sometimes you might have heard CIP PT, that's cast in place PT. So what exactly this PT and PSC mean? So prestressed concrete can be categorized into mostly three parts. There are more to it. I'm just trying to generalize this for this early understanding. So first one is pretension. So what happens in pretension is that we first stress. We'll look into this through pictures. I have some pictures for this. But in pretensions, what happens is that before we cast the concrete, so how do we cast the concrete? Before we cast the concrete, we make the formwork. We put all our reinforcement skeleton inside, and then we pour the concrete, right? So in reinforced concrete, we just put our reinforcement the way we want, and then we pour the concrete. But instead of just putting the reinforcement unstressed, in pretension, what we do is we stress the bars and then pour the concrete, and then we release the strands. We look through the pictures, and then it will give us a better understanding. So that's why, since we stress it out before we pour the concrete, it's called pretension. The other type is PT, but PT can be again bonded and unbonded. So in PT, what we do in post tension, we first we sometimes, if it is a unbonded, we can just put a sleeve or some duct in there, and then we pour the concrete. We let it harden, and after that we pull the strands. And if it is a bonded, then also we put a duct and kind of first we pre-stressed strands inside, then we put the grouts inside, then we pull the strands, and then we release the strand. Then after that, it kind of acts similar to pretension. There are for various reasons we have all these needs. We can always have precast. For example, this structure, if we look at, we cannot have precast here because of various needs. Sometimes we can have probably partially precast, but definitely we need some kind of cast in place connection. For example, the ramps, they are kind of going to be built in different construction stages, and we have to tie them up. So we definitely need some kind of cast in place. So in that case, we need something to be stressed on the field, on the site. So that's why we have that post-tension bonded and post-tension unbonded. Let's look at the pre-stress through pictures. So if you can see on the top left, before we cast, we have the formwork kind of skeleton ready. You don't see the formwork there. So we lay our strands, we lay our skeleton of the structure the way we want. And then we erect the formwork. And then you can see on the right side, actually in the top middle, you see that there are some anchors right here. So these are connected. And then you can see a computer, actually it's connected to a load cell so that we can monitor the load. The picture you see, it's from a precast bed. We call it precast bed. So before we pour the concrete, we pull these strands. How do we pull these strands? Using a jack, hydraulic jack. So we basically know how much, so we calculate all those things. And we know how much we want to pull, how much exact force we want to pull, and it's very precise. It can be in decimals of a pounds or decimals of a kg. So we very precisely pull this, and then when we pull, we use these anchors to hold that force. So we keep holding that force, and while those strands are being pulled, we pour the concrete. And then sometimes if it's a very sensitive structure, we want to minimize the loss or we want to see what's going on. Sometimes we put our instrumentation, strain gauge, load cells, LVDTs, all those instrumentation we put there if needed. Or if it's a controlled, at least when we make a huge batch, we want to make a couple of samples controlled to make sure that all the losses are within the limits. And so while these strands are being pulled, we pour the concrete, and then after a couple of days, then we let it to cure. We put a burlap to minimize our heat of hydration, and then the strands are still being pulled. And then when we think that the concrete has reached enough strength, then we break those strands. So what will happen if we break those strands? This bed was holding that strand with some force. if we cut those strands, then these strands will be free at the end right here, and then definitely this force will be transferred to this concrete structure, and that's actually exactly that prestressed force is. So there are a couple of terminologies involved here. We'll go through it, but I think in this picture we can probably talk about that. I told that there is an early strength, right? Definitely, since that force will be transferred to that concrete structure, so we want to make sure that the concrete is able to take those stress. So we call that if the structure has attained initial strength. So if that structure has not attained initial strength, so how do we know, since we cannot like take a part of this structure, how do we know if the structure has attained initial strength? So what we do when we pour concrete at this stage, we make some samples, some concrete cylinders, and then we kind of cure it, and then we break that cylinder. And then once we make sure that the concrete is okay, it has attained initial strength, then we cut it. And then after we cut it, then you can see we deform it. And then, so what will happen is that when you will look through a picture, but if your strands are on the bottom, so the force will be somewhere here, right? On the bottom, on the both sides. So if the force are on the bottom on the both sides, obviously this beam will try to bend like this, right? So there is an initial deformation here immediately after release. We call it camber, initial camber. So obviously a couple of things come into play here. Because of the prestressed force in the initial prestressed force in the strand, the beam try to buckle like this, right? And that is then it develops something called camber. And but again, because of its self weight, right, there is a uniformly distributed load in this direction, so it will try to bend like this, right? So some of the camber will be neutralized by the self weight deformation, right? So all these things come into play when we do when you really dive into the prestressed concrete. You look after all these things. So this was about bonded prestressed concrete. Since we bond the concrete and then we release the strand, so that's why it's called bonded prestressed concrete. Now let's look at how does the PT looks like. So PT, actually the concept of PT is similar. So we can understand through this picture. So in actual bonded pre-tension, what we do, we directly pour the concrete into the strands. So actually these strands, they directly come in contact with the concrete when we pour. But it's possible that instead of doing that, what we can do is that we can probably put a duct, and then instead of directly pulling the duct, what we will do, we'll put the strand inside, and then we'll pull the duct. So you can see here actually there is a duct. So you can see these are the ducts right here, and then in that duct we will run the prestressed strand. And then what we will do, if it's a bonded PT, we will fill this duct with some grout material. So we'll pump the grout, and then it's similar to prestressed pre-tension strand. So we will, once it is pulled, then we'll pour the concrete. So you can see here actually, and if it is actually unbonded, or and if it's actually like cast in place with very tedious and curved horizontally, vertically, then this PT is preferred. So you can see on the actually right side picture, after you pour the concrete, then what you do, you just then pull, then you pull the structure. So that's why it's more like it's little more versatile. And then again, here also the same thing comes into play. Before you stressing, you want to make sure that your structure attained enough strength. This is one good picture where actually you can see both pre-stress, unbonded, bonded, everything. So you can see that this is a bridge. This is a probably I think 70 or 80 feet half scale structure. So you can see that these are the pulled pre-stressed bonded strand in the longitudinal direction of the bridge, which helps again with the tension on the bottom. But again, you can see there are some in the transverse direction that especially at the end at the bearing locations, the structure is pulled transversely using these anchor sleeves. So what we do here is that we just put a duct here, or probably this threaded rod, and then we put all these things before we start applying the load. And what we do is we kind of screw these threads and then apply our intended force. Again, we can control it using load cells. We can control it using strain gauge, and we can see what amount of force we are applying, both in longitudinal and transverse direction. Okay, one thing here to notice that once we cut these strands, definitely we don't have a lot of control on the forces, because the force already is being transferred. And then if anything happens to the structure, let's say there is some loss or anything happens, then we are not able to reload it, because these strands are already they're bonded, right? We cannot pull it anymore. Whereas you can see that if it's unbonded PT, let's say for some reason you want to increase the force, then you can, because these are unbonded, and with some in some controlled environment you can apply that additional force.